Hello, friends. This time we are going to discuss hysteresis and hysteresis loop. So, we would try to understand what is hysteresis and what hysteresis loop means. So, this discussion is in context with the transformers and uh, motors, especially AC motors, that has to go through, reversal of voltage and the current. As you know, the frequency of AC supply is 50 hertz, and this voltage and associated current have to, vary, 100 times in a second. So, because of this variation in the AC voltage or current, the magnetic material has also to pass through the reversal of magnetic behavior in terms of if you consider the molecular behavior of the uh, material. So we have to study how does it affect the uh, behavior of the magnetic material when it passes through such cyclic process. So what is a hysteresis loop? First, let's try to understand what is hysteresis. So there is a curve. I would like to show you curve in the subsequent slide first. This is the curve we are talking about. And this curve is a graph between B, that is flux density, on on the y-axis, and magnetizing force on the x-axis. So magnetizing force is represented by H and the flux density is represented by Y, B. So here if you see, when we start uh, with a specimen of the magnetic material that is, undergoing such cyclic process, there is a coil you can consider and the magnetic material is placed within the coil. So, when this reversal of current takes place, this cyclic process starts. So, how does it happen? So, when it uh, this ampere turns, basically H is nothing but your ampere turns. So, current multiplied by number of turns is called magnetizing force. On the other side, it is B. So, as the current is increasing, you know this uh, this flux density in the specimen also increases. Okay, but when the voltage, ampere turns, current starts reducing, this flux density does not go to zero when magnetizing force comes to zero. Magnetizing force has come to zero at this place, but this flux density didn't reach to zero, and this is called retentivity. The material used has retained this much of a flux density. That is why this property of the material is called retentivity. Okay, higher the retentivity, higher will be the magnetism or magnetic behavior shown by that material. Okay, so now how to bring this retained part of this magnetic material to zero? So for that, you will have to reverse the uh, current flow in the um, specimen or the magnetic material. So you have to reverse the direction of current in the coil. So when you reverse the direction of current in the coil, it comes to zero at certain point. Now, the amount of the force that was required, amount of, ampere turns, you can say, or amount of H, that is magnetizing force that is needed to bring, of course, it is in opposite direction, magnetizing force needed in the reverse direction to bring this retentivity to zero is called coercivity, or the coercive force required to bring the magnetism to zero. Now, if you again start increasing this magnetizing force in the reverse direction, this will get magnetized. Your specimen will get magnetized in the reverse direction. And again, if you start decreasing the current in the specimen from the reverse direction, then it will also exhibit retentivity in the reverse direction. So at this point, you can see this flux density has not reached the zero. It is magnetized in the reverse direction and it is retaining the magnetism in the reverse direction. And that is why this is called reverse retentivity. Uh, Again, this retained part of the magnetism could be brought to zero only by applying, magnetic field in the reverse direction. This was the reverse direction. Now this is the positive direction. So with respect to this direction, talking, I am telling the reverse direction. Now you have to apply magnetizing force in the other direction to reverse it. So again, if you want to bring it to zero, you require some coercive force or magnetizing force that will bring this magnetism in the reverse direction to zero. Okay, and this cyclic process goes on, again you repeat it. Now from this point it will go to this point, and again this cyclic process will keep on repeating. So this is what happens in the case of a motor. In the case of a transformer, the core material that is made of the silicon steel, that material has got a better permeability. That is why we are using silicon steel in the case of transformers or induction motors. So this allows them to magnetize and demagnetize quickly and have a lesser loss, because this process of reversing the magnetism, bringing it to zero, then again magnetizing it, it consumes a certain amount of energy, electrical energy, and that is why some loss is associated with this cyclic process, and that loss is called hysteresis loss. I hope you have understood this process. Now let's go back to the defining terminologies. Okay, so what is reluctance? Reluctance is the opposition that the magnetic circuit uh, presents to the passage of the magnetic lines of force through it. What is retentivity? You can compare reluctance to resistance in the electrical circuit. Reluctance is a kind of resistance in the magnetic circuit, basically. Retentivity, retentivity is the ability of the ferromagnetic material to maintain residual magnetism, is termed as its retentivity. Okay, so residual magnetism. Now, question is, what is residual magnetism? The magnetism remaining after the external magnetizing force, that is H, is removed, is called residual magnetism. Now, what is coercive force? The magnetic field strength, or H, required to reduce the residual magnetism to zero is termed as coercive force. And now, what is permeability? Permeability is the measure of the ease, ease, how easily. So, it is the measure of the ease with which the magnetic lines of force pass through the given material. Okay. Now, what are the types of the ferromagnetic materials based on this hysteresis? So you have got soft ferromagnetic materials, and there is yet another type of the material that is called hard ferromagnetic materials. Now let's explore what are the behaviors of the soft. ferromagnetic materials. So these materials have thin hysteresis curve as you have been shown here in this left side picture. Now, this type of material have low remanence. Low remanence means its retaining capacity of the magnetism is low. Easy demagnetization as it is low, remanence is low. So demagnetization is also easy. And low coercivity, that means the value of magnetizing force required to bring it back to zero from magnetization is also uh, low. So this type of soft magnetic materials, it can switch polarity frequently and maintains low electrical losses. So electrical losses are low for this type of material. Examples: ferrous, nickel alloy, and ferrite garnets. These are the names of the materials. This is ferrous nickel alloy, basically it's alloyed material, and ferrites are also a certain type of the material that possesses high permeability and so less losses. Applications: these are used in transformers. Ferrite materials are used in transformers for your informations. Applications: two examples of this are transformers and motor windings. Now next is the hard magnetic material. So what is this? Having a broader hysteresis curve, uh, uh, this type of material have high remanence, means retaining capacity is higher as compared to low or soft magnetic materials. Complex magnetization and demagnetization for hard magnetic materials. If the polarity were to change frequently, the hysteresis losses would be incredibly high. So if you want to demagnetize them, probably that is not going to be easy for you. So examples, what are the examples of this type of material? It is steel, carbon is steel, chromium is steel, and tungsten. Now, what are the applications of uh, these hard magnetic materials? So, exerts their magnetic field on the soft magnetic materials because of their wide uh, hysteresis curve. So, you can use them in making permanent magnets, basically. So, what is magnetic permeability? That I have already defined. I'm reading it once again. Magnetic permeability is the value that expresses how well the magnetic material responds to the applied magnetic field. If the dipoles within the material's orientations line up with the external magnetic field quickly, it has high permeability. However, if the dipoles do not well to the applied magnetic field, it is having low permeability. And what is magnetic energy? So this reversal of magnetization, demagnetization, this cyclic process consumes energy, and that is why some amount of energy loss is associated with this. The magnetic flux B at any point on the demagnetization curve of the permanent magnet multiplied by magnetic field strength is called the magnetic energy, BH. So it is much like V multiplied by I, which happens to be the power in the case of uh, AC power supply or DC power supply. So basically, V into I into cos phi, if you consider the power factor, so the power becomes like V into I into cos phi. So BH is also similar to that. BH, this multiplication of V and H gives you the power consumption required for the demagnetization of the magnetized material. So that's it for this. Thank you very much. Stay tuned with me and keep on watching my YouTube channel. Tech Guru Gautam Prasad. Have a nice day.